Good afternoon, everyone. We are the group number six, and today we will discussing the Cohen-Coon method, a powerful and practical technique for tuning PID controllers. This method is introduced by Cohen and Coon in 1953. Is particularly effective for systems with significant time delays and has stood for the test of time as one of the most widely used tuning methods in process control. To start, the Cohen-Coon method is specifically tailored for first order plus dead time systems or FOPDT systems. These are systems where the dynamic behavior can be approximated by a first order response combined with a measurable delay. The key goal of this method is to determine the optimal proportional integral and derivative parameters for a PID controller using the system steps response data. What makes these methods particularly valuable is aggressive starting point for tuning by achieving a quarter amplitude damping response. It ensures quick disturbance rejections. However, this also means that additional fine-tuning may be needed to balance performance and stability. For advantage and practical use, this is one of the most significant advantages of the Cohen-Coon method is its flexibility, unlike the Ziegler-Nichols methods, which is limited to systems with short delays. Cohen-Coon can handle processes where the delay is up to twice the time constant. This broadens its applicability considerable. Moreover, it provides provisions for a PD controller, which is not something most tuning methods offers. That said, if the controller objectives prioritize robustness over speeds, reducing the controller gain can help achieve better stability. For assumptions and conditions, now let's consider the assumptions and conditions that govern the Cohen-Coon method. First, is it designed exclusive for FOPDT systems? This means that a system behavior can be modeled as a combination of first-order dynamics and a measurable time delay. Second, the method relies on step response analysis. The step input should only be applied after the system has reached a steady state to ensure accurate measurements. Additionally, the method assumes that the process is linear and self-regulating, meaning it establishes naturally without external intervention. Finally, the method was originally developed for non-interactive PID controllers, while it can be adapted to other controller structures such as an interactive or a parallel algorithms. Adjustments may be required to ensure the proper implementation.
Well, this method consists in four parts. The first is to ensure the process plant preserves the steady conditions. The second is to apply a step to input signal. Later, the determined delay time in that the L is this and T is the time constant and DC gain KDC from the step response output. So the step four consists of determining the controller P, PI, or PID parameters from the response parameters, delay time, time constant, and DC gain KDC. Okay, for the pressure, we have a four-part important that is to obtain experimentally the response of the plant to a step input. A response may look S-shaped if the plant neither contains iterators nor dominant complex conjugate poles, and the S-shaped curve may be characterized by the three parameters that we mentioned, that is L, T, and KDC. And so the transfer function may be approximated by a first order system 8 and transport law as follows. We have two equations in that the first we have the gain divide to 1 plus the TS. And so the multiplicate of G1 and GD, forget the GS. And the GS has one formula that is that we explained. So for the Cohen current tuning formulas table of controller for PI or PID, we have a key. KP, GI, and TID. Is that so we are seeing several of equations that is important for these for get these parameters.
From this method, we have the following example. The unit step response of an open loop system GS is shown next. Use the Cohen-Coon tuning method to determine the PID controller transfer function. Looking at the graph we have here, we can see that the delay time L is 1.8 seconds. The timing constant is obtained at 63% of the total chain, but the delay time must be eliminated, so giving the value of 2.1 seconds. Finally, the DC gain is the total chain 4. From this table, we obtain the formulas for the PID controller. Exactly, we use these formulas for the PID controller. Then with the value we previously obtained, we calculate the value of the KP, TI, and TD. As we can see, KP had a value of 0.4514, TI had a value of 3.367 sec, and TD had a value of 0.5663 sec. Then with the value we previously calculated, we replace this value in the transfer function of the PID controller. We perform additional calculation for simplify the transfer function. Additionally, calculate the function for the plant. Thanks for watching.